Whoop. The meeting is being recorded. Got it. Yeah, so maybe we should get started. It's really a great pleasure to welcome today's speaker, Nigel Goldenfeld. He's zooming in from the West Coast, so he got his PhD from Cambridge, and after a brief stint as a postdoc at UCSB, he moved to UIUC, where he was, I just learned, for 36 years. And then he just moved to UCSD very recently in 2021. So Nigel's work has spanned really an incredible diversity of fields, and I have personally heard spectacular talks about the statistical mechanics of geometric hallucinations, a renormalization group approach to understanding speciation and evolutionary trees. And I know he's done excellent work in superconductivity and understanding selfish genetic elements, and recently COVID, and what we're going to hear about today, turbulence. Many of you probably also know Nigel from his textbook on the renormalization group, which is very close to my heart. I've taught from it 3 times now. He also has a life in the private sector, which I'm not qualified to explain in detail, but he co-founded a company, Numerics, and he's won a lot of awards recently, including being elected to the National Academy and the Kadanoff Prize. So it's really a great pleasure to have him here today, and without further ado, let's join me in welcoming Professor Nigel Goldenfeld.
Thank you very much for your kind introduction, and let me share my screen and find my pointer. All right, and then move the meeting controls. If anybody has any questions during the talk or your point of clarification, go ahead and feel free to ask, but I've hid the meeting controls, so I won't be able to see them. And if somebody, Ben, could you just keep your camera on so I know that there's a live people at the other end of this talk? All right. So so it's a great pleasure to give this talk at Yale. And part of the reason is because I'm going to be talking about the application of statistical mechanics to turbulence, and some of the the greatest work in this field was done at Yale, and of course some of the greatest work in statistical mechanics was done at Yale too. So in some sense, this talk brings together Gibbs and Lars Onsager, and so I'm super happy to be able to give this talk to you, but I'm sorry that I'm not able to be present in person. All right, so let me hide the meeting controls again. So here's my title. Here are my collaborators and funding. And let's proceed with some propaganda. So let's start off with, why do these meeting controls keep coming up? You just stay away and don't come back. Right. So are new people joining this colloquium? Is that what's going on, Ben? Yeah. Okay. Well, anyway,
I don't see these.
Okay. Well, all right. So I think new people are joining. Wasn't it? Yeah. Another one just joined. 63 people. Okay. Great. All right. So let's start off then with Richard Feynman. I'm going to give you some quotes from Feynman's lectures on physics when he introduced. Gosh, I'm sorry. This is really distracting. Every time people are joining, these meeting controls show up, and then I can't see my screen. So, all right. So somewhere in the middle of volume 2 of the Feynman Lectures on Physics, Feynman writes the following. He says, we've written down the equations of water flow. From experiment, we find a set of concepts and approximations to use to discuss the solution, vortex streets, turbulent wakes, boundary layers of the Navier-Stokes equations. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out or what new qualitative forms are a consequence of the equations. And you've noticed that I've highlighted the words qualitative here. Of course, Richard Feynman was a real master of quantitative physics. His work on quantum dynamics is probably the most accurate physical theory that we have ever developed. But here he's found it very important to talk about the qualitative features of this is just amazing here. Sorry, my screen is just going crazy with these pop-ups. The next thing he says is the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see that the water flow equations contain such things as the Barbour pole structure turbulence that one sees between rotating cylinders. And then he goes on and talks about frogs and Schrödinger and stuff like this. So the point I want to make is that what Feynman was talking about was the qualitative behavior of fluid mechanics. And of course, the qualitative behavior of matter is the domain of statistical mechanics. And so what we're going to do in this talk is we're going to try to understand the qualitative content of the equations of fluid mechanics by understanding phase diagram and the scaling laws of turbulence. And you'll see that by coming at the phenomena of turbulence from a rather novel perspective, we're actually able to make novel predictions and develop new perspectives. And we've made new predictions, and these have been verified experimentally, and I will be showing you that in the talk. So let's start off at a very basic level. Let's imagine that I told you we're going to be doing deterministic classical mechanics of many particles in a box, and you write down a computer program and simulate that, and what you find is that, lo and behold, you recover the phenomena that you are used to seeing in statistical mechanics. So now suppose I say we've now got an infinite number of particles in a box. So now the equations of motion, Newton's equations, become field equations for a coarse-grained velocity field. And here I've written down the Navier-Stokes equations, including terms that take into account dissipation, this term over here. And we'll talk about these things in a moment. For most of what I'm going to be telling you about, we don't need to know what the Navier-Stokes equations are in detail. And so you might not be surprised to know that in this case, the solutions of the Navier-Stokes equations also obey statistical mechanics. And in the typical flow configurations that we're going to be interested in here, as shown on this slide, what we're going to be focusing on are open systems. And so if we're going to be obeying statistical mechanics, it's going to be non-equilibrium statistical mechanics, which of course doesn't really exist yet. So the sort of flows that I'm going to be studying are typified here. They're all flows where the fluid comes in from the left, departs from the right, undergoes either perfectly steady and predictable flow as shown over here. We call that laminar, or fluctuating unpredictable flow as shown over here. We call that turbulence. And then somewhere in the middle is the laminar-turbulence transition that we're going to be discussing for pipes. And in pipes, this occurs at a Reynolds number of about 2000. And we're going to discuss this in great detail in this talk. So the Reynolds number here is our control parameter. It's just the characteristic velocity of the flow, characteristic dimensions divided by the kinematic viscosity nu. So when I talk about life and death of turbulence in my title, by life of turbulence, what I mean is this Reynolds number flow regime here, where we start to see turbulence, and we're going to try to understand some of its properties. And in this regime here, we're going to see that turbulence actually can die as we go down in Reynolds number, and we're going to try to understand why that is. Now, the other thing that that you'll see here is that I'm not using the last refuge of the scoundrel or theoretical physicist, which is periodic boundary conditions. All of these flows are open, and the reason for that is that turbulence is fundamentally about instabilities. It's generated at boundaries, and the fact is that symmetry is the enemy of instability. And if you want to understand the way that the instabilities develop and then to create mean flows, which then interact back on the turbulence and cause the fluctuating flows that we see, one really needs to have a handle on the instabilities. And so that's what we are going to be focusing on in the way we describe turbulence. Now, what does it mean to say, let's solve turbulence? I mean, we all know that turbulence is the last great unsolved problem of classical physics. So what would it mean to solve it? So one answer might be, if you walk down the street, find a physicist, ask them, what it would mean, they'd say, well, maybe you should try to predict the fluctuations at small length scales, because after all, turbulence is about fluctuating velocity fields. So maybe we can understand something about those small scales. And the physics of that is what's known as the energy cascade, which I've illustrated here. The idea is that you put your fingers into the bathtub, you stir them around, and that creates swirly, whirly eddy things that then spin off other eddies, and they go to smaller and smaller scales, and as sort of sketched schematically over here. And that process doesn't involve friction. That process is a dynamical process. It's a Hamiltonian process. And the understanding of why that is was really developed by Richardson in the 1920s, and then later developed by Kolmogorov, as I'll show you in a few minutes. But the main thing I want you to understand about this cascade process is that it's not a dissipative process. It's not some structure that sort of breaks up and breaks into smaller and smaller pieces. This is actually the dynamics. And so this is not a process that's driven by viscosity. And so we might expect then that this process will be independent of viscosity. Now, exactly that kind of analysis was first done by Kolmogorov, probably the greatest mathematician of the 20th century. And here is what he did. So he said, let's look at the kinetic energy, E, per unit wave number range, K. So K is going to be wave number, E is turbulent kinetic energy. And we're going to ask, what is that going to depend on? Well, obviously it's going to depend on K. It's going to depend on epsilon, which is how much energy you're putting into your system, how vigorously you're stirring it around. It's going to depend on the kinematic viscosity, nu, and it's going to depend on the system size. Now, out of these quantities here, you can construct a length scale called the Kolmogorov length, which is constructed from the kinematic viscosity and the energy flow through the system epsilon. And so now we can write the energy per unit wave number range in the form shown over here. So now that's all dimensional analysis can do for us, but now we're going to proceed by making two approximations. So the first approximation we're going to make is that we take the system size to infinity, but keep the wave number fixed. And when we do that, KL is then going to go to infinity. And so what we'd be tempted to do is say, well, let's just replace KL over here by its limit value infinity. And now we've reduced the number of variables in the problem from 2 to 1. Then let's now suppose that we take the high Reynolds number limit. So we're going to take the high Reynolds number limit, and that occurs when the viscosity is low. If the viscosity is high, then of course you have a viscous fluid, it's not turbulent. If the viscosity is low, then you will have a turbulence. So formally, the turbulent limit, the Reynolds number goes to infinity limit, occurs when the viscosity goes to 0. So we take that going to 0 as well, and so Ke2 is going to 0 over here. But not so fast, because the problem is that eta is also outside here, and so is the viscosity, the kinematic viscosity outside here. So in order to take this limit, we have to make an assumption about what is going to happen in order that the viscosity can cancel out in the front and inside this function. And the only way that can happen, that limit can exist, is if the viscosity cancels out, and that means that this function must be a power law function of its argument. So when you go through and do that calculation, it's just a couple of lines of algebra, what you'll see is that indeed it cancels out as long as this function goes as 1 over its argument to the power 5/3, and so you end up with this form here. And this is the famous Kolmogorov's 5/3 law. Okay, so that's a fantastic prediction. It says that if I look at the energy spectrum, as we call it, of turbulence as a function of wave number, it's going to have this form like this. This is the scale where you're putting energy in. This is the scale where energy is being dissipated as Joule heating. And in between, there is this power law regime, the so-called the inertial range, where the energy spectrum should go as k to the minus 5/3. Okay, well, that's one of the most important arguments made in the history of turbulent studies, but it's not quite correct. And the reason it's not quite correct is that this assumption is not correct. from in the Russian mathematical literature, we would say that this is incomplete similarity, namely that this limit process here is not of a well-defined limit and should be replaced by its asymptotic form KL to some power eta, where eta is a critical exponent known as the intermittency exponent. So if that happens, then what happens here is that this power law 5/3 is going to be modified by this expression here, and that's going to be a small correction, and we'll say more about that later on. Okay, so that's one argument that you might use to say if we could understand turbulence at small scales, we would understand this in more detail from the Navier-Stokes equations. Another argument might be, well, why don't we try to understand the dissipation experience at large scales? Because I'm an engineer and I'm trying to design a car or a plane or a pipeline, and so I want to know what is the drag that is created by turbulent flow. So here's the answer to that. So this is a data taken by Nicorazzi in 1933. Plotting on the vertical axis here is the friction factor, which I'll tell you about later, but it's basically the pressure drop normalized by the kinetic energy, i.e. the velocity squared. So this is friction, and then this is a Reynolds number along here. And he did this in a sequence of pipes, which was the smooth pipes have the lowest friction, and then pipes with increasing roughness, so they had the larger friction. Now, normally you would say that the friction experienced by a fluid is proportional to how fast the fluid is going, but we're normalizing by the kinetic energy here. So that means that on this graph, the Stokes drag, as it is called, would go as 1 over the Reynolds number, and that's what you see over here. Then you see a transition to turbulence, which remains to be discussed. And then, as you see here, what happens is the friction is a non-monotonic function of Reynolds number and roughness, and eventually at large Reynolds numbers becomes independent of Reynolds number, but just depends on the roughness. So that's the curve. And we're going to say more about that later. But the thing that you might want to say then is, well, can we connect the scales? Can we show how the fluctuations at small scales give rise to the friction at large scales? And if one can, then we'd be able to understand something about the connection between fluctuations and dissipation in a turbulent system. So another thing that you might try to say is, well, if we want to understand turbulence, maybe we ought to be able to predict when and how fluids become turbulent. And this is indeed what Werner Heisenberg's PhD thesis was about. So the first experimental study of this that was done scientifically was not by Heisenberg, but was by Osborne Reynolds in 1883. And what he did was he took a pipe, injected fluid into it, and then put a little dye in the fluid, ink, and looked at the pattern that was traced out. And what he found was that at small speeds, the flow was smooth and regular, which is laminar flow. At high speeds, the flow after an initial period became ragged and irregular and turbulent. And in between, there was this transitional flow where you had patches of turbulence, which he called flashes, and today we call puffs, interspersed by regions of laminar, then turbulence, then laminar, then turbulence, and so on. And so the transition to turbulence was rather a surprise. Now, the most basic question that you could ask about turbulence would be, if it's going to be no turbulence at low Reynolds numbers, it's going to be fully turbulent at high Reynolds numbers, what is the turbulent fraction? How much turbulence is there in the pipe as a function of Reynolds number? And these are data, which I'll talk about in a few minutes. These are data taken not on pipes, but on a quasi-one-dimensional flow called a Taylor-Couette flow, a specially constructed one. And you can see that the data come up in this way. Notice that this transition is not spatially uniform, and that's going to be important for what I'm going to say next. All right, so what is the quantitative description of the transition to turbulence? So what I've shown you so far is I've shown you this turbulent fraction as a function of Reynolds number, and you might say that that's kind of reminiscent of the way that an order parameter grows as you go through a second order phase transition. The other thing I've told you so far is that the energy spectrum, in which I can write down as the order correlation function of the velocity fluctuation, so it's a correlation function. The energy spectrum shows this power law regime in this intermediate scale, again reminiscent of what you see at a critical point. And so you might think that there's a connection between turbulence and phase transitions, and you'd be right. Let's talk about this question. Why is turbulence still unsolved? Well, because there is this sort of connection that you can see here. And maybe we should ask the question a different way. Why is the phase transition problem hard? Well, the phase transition problem is hard because you have strong interactions. You have fluctuations. Those fluctuations in the order parameter are non-Gaussian, and you get strong bursts of fluctuation, so it's somewhat intermittent. But the real reason that the phase transition problem was hard and took so much time to solve is because there is no usable small parameter. So here we can write down the Landau free energy for a typical transition, as most of you, I'm sure, are familiar with. And you might say, well, of course, there's a small parameter. It's just T minus TC over TC. That obviously is getting small as we go towards the transition. But if you take this field theory and transform it into dimensionless form near the transition, what you'll find is that the coupling constants, the quartic term here, which is the interaction between fluctuations, turns out to go like this. And what that means is that if I'm in spatial dimensions less than 4, this coupling constant actually goes to infinity and not to 0. And so the point is that the coefficient of the interaction becomes relatively large as the phase transition temperature is reached, and so we don't have a usable small parameter after all. Now for turbulence, we also have strong interactions and fluctuations, this time in the velocity derivatives. The system has very non-Gaussian fluctuations. They're very intermittent. And the point is, as you'll guess, that there's no usable small parameter. Here's the Navier-Stokes equations that I've written down to you before, basically Newton's equations of motion with their dissipation shown over here. This is the kinematic viscosity. The only nonlinearity in the problem is this term here, which is advection. And you can see that as I take the limit, nu goes to 0, this term coefficient stays 1, whilst this one goes to 0. And so this coefficient of the nonlinearity becomes relatively large and goes to infinity as the viscosity goes to 0. And so again, we don't have a usable small parameter in the problem. So this might suggest to you that since the critical phenomenon problem was solved by Ben Widham discovering data collapse, Leo Kadanoff discovering and explaining data collapse and introducing scaling concepts, and Ken Wilson introducing a renormalization group theory, you might think that we could use some of these same ideas in turbulence. And as you'll see, we certainly can. Okay, so now I want to talk about the transition to turbulence, and then in the second part of the talk, I'll talk about what are called fluctuation dissipation relations. So this is how turbulence is studied, at least the transition to turbulence, in the 21st century. So what you do instead of what Reynolds did is you take a pipe, you create a laminar flow very, very carefully so that it's flowing around about Reynolds number 2000 and it's laminar. And then you introduce a disturbance into the flow, and that disturbance creates a localized region of turbulence, a puff, and that puff then propagates down the tube until it comes out the other end. Now, the question we're going to ask is, what is the survival probability of turbulence? So as the turbulence is propagating down the pipe, it can either do one of two things. It could either just die away, in which case the fluid will come out the pipe a little bit faster, and so it'll follow the yellow trajectory, or the turbulence might persist until you get to the end of the pipe, in which case it will come out slower and follow the red trajectory. All right, we know how fast the fluid is going. We know how far the disturbance entry is from the end of the pipe. And so we can compute the survival probability as a function of Reynolds number and time. And that was first done, at least in the most accurate way, the most correct way, by Björn Hoff in a seminal paper in 2008. Now, here's what Hoff found. We start off with a turbulent puff, shown here from a numerical simulation showing the turbulence intensity. And as a function of time, this thing decays away. And so the laminar state is the stable one. The survival probability as a function of Reynolds number over here and time along here, follows these data shown here. These are very early data. And so it basically has an exponential dependence. This is a log linear plot. So it's a memoryless process. We can read off from this exponential behavior a lifetime tau, and that lifetime tau is plotted against Reynolds number over here. And you can see that this is a lifetime that increases rapidly with Reynolds number. And in fact, since this is the logarithm of the lifetime up on the vertical axis, we can see that the lifetime is actually increasing faster than an exponential function. Now, when we go to slightly higher Reynolds numbers, maybe above 2050 or so, our puff, instead of just dying away, actually can split into two. And then the two new puffs, the original one and the daughter one, can either split or decay and so on and so forth. And so then you might ask the following question. Well, what's going to happen if I ask what is the time it takes for a puff to split? And what you find is that that time decreases as the Reynolds number increases, because as you increase the Reynolds number, the flow is trying to become more and more turbulent, so the puff splits quicker. And this also is a curve that curves upward and so is increasing faster than exponential. And indeed, if I take the double log of these data, and you might say that's the last refuge of the scoundrel, and you'd be right, but there is a theoretical reason for this. If you take the double logarithm, you see that the data fall on straight lines, and they intersect at a Reynolds number, which we identify as the critical Reynolds number. And we identified this as the critical Reynolds number because above this Reynolds number, for a long pipe, there's always going to be a finite probability that a puff has split, and so there'll be some non-zero turbulent fraction in the pipe. So what I've told you so far is that turbulent timescales are controlled by timescales that grow super exponentially with length. Okay, so now let's make a theory for this. And for this theory, we're going to follow what we do in regular equilibrium, statistical mechanics. So let's just remind ourselves what we do there. So now we're going to talk about a magnet, an equilibrium magnet. And the important thing I want to talk about is the concept of levels of description. Because what I want to show you, remind you, is that when we study phase transitions, we typically aren't able to solve the problem from first principles. And I'm saying this because when we get to turbulence, and you might say, well, how do you solve this problem from the Navier-Stokes equations? I'm going to say, no, we don't need to do that. We're going to do something a little bit smarter than that, and I'll tell you what that is in a minute. So with a magnet, we might say the lowest level of description that's relevant is the electronic structure. That's too hard to solve. So then we make a classical Swin model of that. That's the Ising model. And again, that's insoluble unless you're in 2 dimensions and your name is Onsager and there's no external magnetic field. Other than that, that model is also too hard to solve. So then you write down the Landau theory, which we saw on the previous slide, and then from that we can work out the renormalization universality class. And we know that there's 2 stylized facts that are important for the transition in a magnet. There's the order parameter behavior near the transition point, where you have weak long wavelength modes that contribute to the non-analyticities of the problem. And the magnetization grows with some strange exponent beta, which is not equal to 1/2 as you go below TC for H = 0. On the other hand, I could set exactly at TC and vary the external magnetic field. And normally you would expect that the induced magnetization would be proportional to the external field, but that linear response breaks down at the critical point, and in fact, M scales with the external field in some non-integer way with a new exponent delta. And what Widom and Kadanoff discovered was that this can be all accounted for if the magnetization, ostensibly a function of 2 variables, is really a function of some new single variable. And here is shown how well that works. This is the magnetization plotted in the way that the renormalization group predicts. This is the temperature scaled in the way that the renormalization group predicts. These are 5 different magnetic materials. The data are all plotted in this way and fall onto one universal curve. And here is the renormalization group prediction for that universal curve with no adjustable parameters. So that's a great success. It shows you that this model gives you a really precise prediction in agreement with experiment. Except it's not actually a model. It's a model of a model of a model of a model of a model. We started off with quantum chemistry, went to electronic structure, we made a quantum Heisenberg or Ising model, a classical Heisenberg or Ising model, and then we made Landau theory. And every step along the way here was a non-systematic approximation, which could not be justified a priori, but then post hoc one could justify them using the ideas of relevant variables and so on from a renormalization group theory. So now when it comes to studying turbulence, we should expect to encounter similar difficulties. It would be crazy to think that you could start from the lowest levels of description and be able to do something for something as complicated as fluid turbulence, which is out of equilibrium, something that we couldn't do for magnetic systems. So the question that we're going to ask is not how do we solve Navier-Stokes near the transition, but what is the analog of Landau theory for it, and what is the renormalization group universality class? And of course, we're not going to be literally doing Landau theory because we have a non-equilibrium system here. So we're going to be asking for a Landau spirit type of description, namely the lowest order non-equilibrium description that accounts for the main phenomenon. So in order to do that, we have to try to understand what are going to be the long wavelength collective modes at the transition, and we don't know how to solve that problem analytically, so we have to do it numerically. So what we did was direct numerical simulations of the Navier-Stokes equations for a puff in a pipe. And we looked at that very carefully and tried to see what are the modes that are going to be behaving in a singular way near the transition. And what we found, to cut a long story short, is that there's really two modes that are important. So at small scales, there is the turbulence, but at larger scales, there's an azimuthal mode that goes in the azimuthal direction around the pipe. It's time dependent and has radial structure as shown over here in this snapshot through the cross-section through the pipe. This mode will call a zonal flow for reasons that don't really matter for now, but the zonal flow and turbulence fluctuate in energy as shown over here, and you can see that they are somewhat out of phase, roughly about 90 degrees out of phase. Now, what's actually happening here is rather interesting. What's happening is that at small scales, turbulence is creating some sort of fluctuating flow field, which is anisotropic. And that anisotropy then shoots out sort of little jets of turbulence that get to the walls and start circulating around the walls of the pipe. And that anisotropy in the turbulence then causes there to be a flow, this zonal flow that goes around the outside of the pipe. Now, what that flow does is it shears the turbulence, and by shearing it, it suppresses it. So what I told you is that the turbulence induces this azimuthal zonal flow that then shears and isotropizes turbulence, and by isotropizing it, it reduces the source terminus equation here. Once it's reduced the turbulence, then that's going to suppress the zonal flow. And once the zonal flow is being suppressed, then the turbulence can then rise because it is no longer being smoothed out. So what I've told you is what you would have seen if you looked at a completely different problem, the problem of a predator and a prey in an ecosystem. What happens in an ecosystem is that you have a prey, let's say a wolf or whatever this creature is, a lynx, and what it does is it tries to eat its prey, a sheep or a hare in this particular case. And so what happens is that the prey population goes down. Once the prey population goes down, the predator population has to go down as well because they're running out of food. But once they run out of food, then the prey population can then go back up again because they're not being eaten by the wolves. And so you have these population cycles, these persistent cycles, and these are called predator-prey or activator-inhibitor cycles. And so what we've seen then is a suggestion that pipe flow near the transition to turbulence looks like a predator-prey ecosystem. So how do we model a predator-prey ecosystem as a statistical mechanic? Well, what we don't do is open up a textbook on ecology and look at the differential equations that describe predator-prey ecosystem, the so-called Lotka-Volterra equations. And the reason is that the simplest form of those don't describe population cycles. And why they don't is a very subtle point that I'm not going to talk about, but somebody can ask me if they want at the end, but it involves anomalies, such as the anomalies you get in field theory. So what you do instead is you say, let's make a stochastic individual level model of a predator-prey ecosystem. So A are going to be predators in red, B are going to be the prey in black, and E is the food or the available space. Now what we do is we write down reactions that tell us what happens when a predator runs into a prey. So here's a reaction, for example, a predator A runs into the prey B, and with some probability P, eats the prey, and then uses the energy thus gained to create a baby predator. So A plus B goes to A plus A. And you can do all the other possible things that could happen with these other reactions here. And when you simulate that in a computer, what you'll find is a stochastic, persistent oscillation in the system. So if we're going to try to make a Landau theory for transitional pipe turbulence, then we're going to build it from stochastic predator-prey dynamics. Now, the way we might go about doing that is to use the Feynman diagrams that correspond to turbulence, which were first written down by my colleague at Illinois, Bill Wild, in the early 1960s. So what you do is you take the modes that are important, in this case, the zonal flow and the turbulence at small scales, and you write down the possible interactions between these lines here. The Navier-Stokes equations have a quadratic nonlinearity, so every vertex in this problem is a triple vertex, and you write down every possible diagram that you can, and we look at the lowest order ones. Now, I'm not going to go into how you write down the Feynman rules for this and so on and so forth. But here you are. This is a turbulence line meeting a zonal flow line. Something happens, and then you get two zonal flow lines coming out. And so this is the Feynman diagram version of what we saw in the particle picture of A plus B goes to A plus A. The predator meets the prey and produces two predators. And the same thing is true for every diagram that you can write down here. There's a dictionary between all of these processes and all of these Feynman diagrams. So now I want to show you that a stochastic predator-prey model recapitulates everything that I've told you so far about the transition to turbulence. So let's start off then with a phase diagram of transitional turbulence. So here is what you've seen already. So here is the Reynolds number, and here is the behavior of the puffs. Now for the predator-prey model, the analog of the Reynolds number is the prey birth rate. So let's think about why that might be. Let's suppose that I have a sheep and they give birth once every 100 years. So the wolves come along, they eat up all the sheep, and then the whole ecosystem dies. Okay, so nothing interesting. But now suppose we increase the birth rate of the sheep to being once every 10 minutes. Okay, so now what's going to happen is the predators are busy eating the sheep, but the sheep are busy making babies, and so you have the possibility of there being a coexistence between the predator and the prey. So when you go and work out what happens if I take a spatially extended predator-prey stochastic system, create a little region of population of predators and prey and evolve it, what happens is you find a little puff of prey and predator will eventually decay if the prey birth rate is too small. This is like the predators eat everything and then everything just dies. On the other hand, if the prey birth rate is high enough, then actually what happens is you get a pattern forming instability, you get a splitting population and traveling wave, just like you see over here in turbulence. And so the predator-prey model does actually recapitulate the phenomena that you see in real turbulence. And here are the world lines of turbulence in both the real turbulence case and in the predator-prey case. So here what is plotted is space, time on the vertical axis, and the color tells you the turbulence intensity. And here you see a puff that's moving slightly backwards in the laboratory frame, and then this time here splits in this way shown over here. Here is a puff in the predator-prey system that then splits and undergoes many other subsequent splitting events. So now we've recapitulated the actual phenomena, we can now go and measure the statistics of the extinction time in the predator-prey case and the statistics of the time between population splitting events in the predator-prey case. So we go ahead and do that. And what we find is the following. Here on the right are the data I already showed you for the turbulence puff and splitting lifetimes. And here are data for what happens in our stochastic predator-prey system. And so what you see from this is that the predator-prey system recapitulates the phenomena that we see in transitional turbulence. The death of turbulence is the same as the extinction transition in ecology. So what I've shown you so far is we started off with classical turbulence. We found that it looks like a two-fluid model near the transition. We found that the two-fluid model had things in common with a predator-prey, a stochastic predator-prey system. But what we really want to understand is the universality class. So now I'm going to show you that the universality class of the laminar turbulence transition is directed percolation. And we're going to see that by showing you that the stochastic predator-prey system here can be written down as a quantum field theory, which was first found in high-energy physics known as Reggian field theory, and that field theory can be mapped into directed percolation. Now, I'm not going to show you this by writing down path integrals and things like this. I'm going to show you just graphically. So let's talk about what directed percolation is. So directed percolation is what you might imagine doing every morning when you make your coffee. You have your coffee grounds in your filter, you pour some water down onto the filter, the water tries to trickle, find its way through the grounds, and then eventually it comes out the bottom and makes your coffee. Now, here are the trajectories that could happen here. P is the probability that you're able to go from one site to the next site, and this is time increasing as we go down here. It's like the direction in gravity in the coffee flow example. So what you can convince yourself of is that if you look at every possible path here, these paths can all be built up out of these four basic motifs. Start off at this time here, and in the next time step, you can either have annihilation, that the flow just doesn't get through, or the flow starts off at one site and goes to the site below and a neighbor, or it diffuses, or you get coagulation as shown over here. And when you go ahead and simulate that, what you find is that if the percolation probability is too small, then the fluid can't get through and so a long time there are no occupied sites. The occupied sites will turn out to represent turbulence, so this will be that there's no turbulence. For large values of the percolation probability, it's easy to get through, and so at long times there is a high turbulent fraction or high fraction of occupied sites. And then at just the right amount of percolation probability, you're just about able to get through to the other side. And so at long times, you have a small fraction of occupied sites. And if you're making a cup of coffee, this here is where the water is not able to get through your coffee grounds, backs up over the counter, and you make a big mess. This over here is where the water quickly trickles through, and you get the sort of cup of coffee that you might get at a gas station. And this is the perfect cup of coffee, where the water takes the longest possible time to get through. And this transition is characterized by critical exponents. So here is the density of occupied sites or turbulent fraction as a function of P minus the critical percolation, going as some exponent beta, and these are correlation lengths, so let's not worry about this. So if I were to simulate that in 3 dimensions, it would look pretty much like what you're seeing on the left-hand side here. And if I take a slice through my turbulent puff, it starts off with fully occupied sites, the turbulence decays, and eventually at some place I get the last remaining pixel that disappears, and the time it takes to disappear defines for me the lifetime of that turbulent puff. So what that means is that the active state, the turbulent state, persists until the longest puff has died, the longest lasting puff has died away. And that tells us that geometrically, this longest trajectory here is the lifetime of turbulence, and so it's going to be dominated by extreme value statistics. meaning that the lifetime of turbulence is given not by the probability distribution of the lengths here, but what is the probability distribution of the longest path. And that can be shown to be given in this particular case by this exponential function shown here, and that is fundamentally the reason why you get that super exponential behavior that I showed you at the beginning. Now, if I want to write down the basic processes that happen in this predator-prey ecosystem near the extinction, here they are. This is everything that you've seen before, with the addition of labels I and J that tell you lattice sites as these things are hopping around in space. So what we're going to do is we're going to ask what happens near the transition. And near the transition, what's going to happen is the predator population is going to be very small because the prey population is small. And so the predators are not going to survive. So we'll just simply cross out every term in these equations that depends on the predator. And now what we're left with are these equations here describing the prey and its energy source, the energy in the laminar fluid, or if it was an ecosystem, the food source. And each of those terms here can be written down diagrammatically like so. And you'll see in these 4 diagrams here, representing each of these terms, the 4 basic processes of directed percolation. And so what we've learned is near the extinction transition, stochastic predator-prey dynamics reduces to directed percolation. So is it true? So let's have a look at the experimental data. Now, back to back with our paper in Nature Physics, Björn Hoff and collaborators did this beautiful experiment where they took a Taylor-Couette cell, which is basically an inner cylinder and an outer cylinder. The inner cylinder stays stationary, the outer cylinder rotates. The cell is very, very narrow like this, and so it's basically quasi-one-dimensional, almost like a pipe with periodic boundary conditions. You have a little slit so you can look at the fluid through the pipe, and as the fluid goes past, it'll look silver when the little scales that you put into the pipe, you put into the fluid to reflect light, are all aligned. The flow is laminar, but when the flow is turbulent, and these little patches here, which are in black, they're all in random orientations, and so they look black. So these black patches are turbulent, and these silver regions are just laminar flow. So the fluid goes past once, and you see this picture here, then it goes past again, then it goes past again, and so on. And most of these pictures look the same, but if I stack them up one underneath each other, you see that they trace out a pattern in space and in time. And here is that pattern in space and time shown over here. Yellow is laminar, blue is turbulent, and you can see that as you increase the Reynolds number, you go from a state which is not able to get through to the other side, a turbulence that decays, to turbulence that does get through to the other side. It persists at long times, and there's an intermediate range where it is just persisting at long times. You can, of course, do very detailed measurements on these trajectories and measure the turbulent fraction, and you see that it fits very well the predictions of 1 + 1 dimensional directed percolation. And just last year, the Hoff group were able to do this in 2 dimensions as well. So we can measure the critical exponents, we can measure the universal scaling functions. Okay, how about the predator-prey dynamics? Well, that was also being observed, not in the pipe, it's very difficult to do it there, but in the magnetohydrodynamics, in the tokamak, you have an analogous phenomenon. You have a drift turbulence that goes around like this, you have a zonal flow that goes around the outside, and there are predator-prey oscillations that were predicted many years ago by Pat Diamond and observed about 10 years or so ago by Estrada. So what I've told you then is that near the transition, the laminar turbulence transition occurs as a non-equilibrium transition, and it's in the universality class of directed percolation, which is astounding. All right, I'm not going to go through what happens near the transition that we've recently studied that problem, and there's a Fisher letter from last year that describes that. Now I want to talk about fluctuations and dissipation. At the beginning of the talk, I showed you data from Nicorazzi's pipe experiment. So what he measured was this so-called friction factor, the pressure drop across the pipe, normalized by rho u squared. And what he did was an experiment that sadly has never been repeated. He took sand grains of different size and pipes of different diameters and glued the sand grains to the side of the pipe to provide a uniform roughness. And then what he did was he measured this friction factor as a function of Reynolds number for different roughnesses. So over here, at the lowest data set are the smoothest pipes, and then as the roughness increases, the friction factor increases as well. So what I want to do now is I want to walk you through the anatomy of these curves and show you two scaling laws here. And what I'm going to show you is that these scaling laws are precisely analogous to the scaling laws I showed you earlier, the Widom scaling for magnetic systems. And we can see that these things are controlled by a critical point, a non-equilibrium critical point. So here we are at low Reynolds numbers, and because of the way that we normalized the friction factor by the velocity squared, the laminar regime has a friction factor decaying as 1 over Reynolds number. Then there is this regime here that we just talked about, the transition to turbulence, and then here is a regime where the flow, sorry, not the flow, but the data flow down, well, I shouldn't use the word flow. The data follow this line, and the smoother the pipe is, the further they follow this line. And this line has a slope of Reynolds to the -1/4, and we're going to call that scaling the Blasius scaling. And as you make the pipes rougher and rougher, they depart earlier and earlier from this scaling law. Then something non-monotonic happens. And then at large Reynolds numbers, the friction factor becomes independent of the Reynolds number, but just depends on the roughness. And it turns out that this dependence here goes as roughness divided by the pipe diameter to the one-third power. So the question I want to talk about now is this a critical phenomenon? And why might you think that it is a critical phenomenon? Well, let me tell you what the chain of argument is. I showed you earlier on that in critical phenomena and turbulence, you have some similar features. The first one I told you about was the energy spectrum of turbulence, where you have this Kolmogorov scaling law, k to the -5/3, at least in mean field theory, if you ignore the fluctuations due to intermittency. In critical phenomena, the correlation function, say, of two spins also decays as power law in k, say, as k to the -2 is shown over here. I also showed you earlier on the data collapse that was discovered by Widom and Kadanoff. And so the question I want to ask now is, what is the analog of data collapse for turbulence? Well, in order to answer that question, we have to know what is the analog, not just of T minus Tc, but we also have to know what is the analog of the external magnetic field in say, a magnetic system. Now, it turns out, and I'm not going to go through the arguments for this, it turns out that the analog of magnetic field in turbulence is the roughness of the pipe. And the reason that I say that is because roughness causes the laminar flow to become turbulent. So it's like it biases the flow in the direction of the order that occurs at large Reynolds numbers. And the analog of T minus Tc going to Tc, going to 0, is that the Reynolds number itself goes to infinity. So when you work out the theory for that, doing a sort of Kadanoff block spin type of argument, what you find is that you predict that the friction factor, ostensibly a function of two variables, Reynolds number and roughness, are actually as a function of this combined function over here. And here is that function plotted in the way that the theory predicts. And Nicorazzi's data all collapse onto one universal curve with an exponent 0.02 for the intermittency exponent, which is consistent with estimates obtained by more straightforward ways. So what I've shown you is that that turbulence behaves as if there is a critical point at infinite Reynolds number and 0 roughness that controls the singular behavior in this regime over here. Okay, so this is the analog then of what we saw for Widom scaling. Now I want to show you what this means experimentally. But the first thing I want to point out is that this is a really amazing discovery in my view, and I feel very lucky that I was able to do this, because What it tells you is this: back in 1933, just by measuring the pressure drop across a pipe, Nicorazzi had actually measured the anomalous dimensions, the critical exponents of turbulence, 8 years before Kolmogorov even guessed the scaling laws for the mean field theory. And this is a connection between the velocity fluctuations, the intermittency exponent, and the friction factor or dissipation. So we called it a spectral link in our work, but it's really an example of a fluctuation-dissipation relation. Now, I'm not going to tell you where these scaling laws come from or how you account for these exponents, but let me just say that you can do that. And this is work that was done in a back-to-back fissure of letter with my own paper by Gustavo Droya and Pinocchi Chakraborty. And what they showed was that the friction factor can be represented as an integral that depends on the energy spectrum. So this literally relates the dissipations to the fluctuation. And from this, you can calculate the scaling and so on. Could somebody please unmute their microphone, please? Thank you. So let me just show you some experimental data that we did to test this idea. And we did the experiments in 2 dimensions. So in 2 dimensions, it turns out that there are 2 cascades. There's the cascade where energy flows from large scales to small scales, as you might expect. But in 2D, and that's an energy cascade, but in 2D, you can also have a cascade of vorticity, angular momentum, if you will, that goes that goes from large scales to small scales, and energy goes from small scales to large scales. So you get 2 different cascades in different directions. And because angular momentum and vorticity have different dimensions than energy, the energy spectrum that corresponds to the forward cascade of vorticity, which in these contexts is called entropy, that has a different energy spectrum that goes as k to the -3 rather than as k to the -5/3. And so from this you can work out what should be the prediction in 2 dimensions for the entropy cascade, this vorticity cascade in a 2-dimensional turbulent flow. And you can see that you make different predictions for these scaling laws. So we did these experiments in 2 places, in Pittsburgh and in Bordeaux. And what we did was we created a 2D flow by a soap film held between a fishing wire, and then saw blades on the right and left-hand side provided the roughness. And then what you do is you put little particles in the flow, you shine laser light off those particles, and then from the reflections you can do laser Doppler velocimetry and work out the velocity field in this flow. So here's an example of what we did in this flow. So here is a fork put through the soap film, creating turbulence, and you can see that the energy spectrum has this k to the -3 scaling that I told you about. In a different geometry, the one shown over here, where there's no fork, but there's just rough wall over here, and you measured near this wall, you can see that the energy spectrum goes as k to the -5/3. And so we can create this inverse energy cascade where energy flows from small scales to large scales. And now we measure the friction factor, and what we find, as predicted, is that for the energy cascade, the scaling goes as Reynolds to the -1/4, but for the entropy cascade, the vorticity, the angular momentum, it scales as predicted as the Reynolds to the -1/2. So these experiments were done about 10 years or so ago. Last year, a year or so ago, they were improved by Hamid Kareh and collaborators, and they were able to measure the Strickler regime. And so here was the friction factor scaling as the first power of the roughness as predicted, and here is the universal scaling function collapse, again agreeing with our predictions. And so what I've shown you then is that the drag experience at large scales reflects the very nature of the turbulent states at small scales. We made 2 predictions, actually 4, all of them confirmed experimentally. So what I've told you then is that really there's 2 types of universality in turbulence. There's a critical point at the transition to turbulence, at least in flows where it is a subcritical transition, such as pipe or Taylor-Correct flow, and that is in the universality class of directed percolation. There's another turbulent fixed point at large Reynolds numbers and zero roughness that controls the fluctuations, dissipation, and various other features of the flow. So here is my summary. I've just told you very quickly all of these things. Let me show you my collaborators. Here they are: Hamid Calais, Gustavo Joy, and Pinaki Chakravorty. Tuan Tran was a graduate student at Illinois who spent 2 years working in Walter Goldberg's lab, and we had weekly lab meetings going on for many hours over Skype. And here is Huangyan Shi, Zonglin Si, and Shiying Wang, who I didn't have time to tell you about her work. This is Huangyan and myself in the basement of the mechanical engineering department of the University of Manchester in England, in front of Reynolds's original apparatus. I want to end with a fortune cookie. And this is a real fortune cookie that I got. And I'm probably the best person in the entire world, the most appropriate person to get this fortune cookie. Because it says, turbulence is a life force, it is opportunity, let's love turbulence and use it for change. And it also gives you some lucky numbers that you can use in your Monte Carlo simulation. Now, the reason that I show this is because what I talked about, at least in the first half of this talk, was how we used ideas from biology, in this case ecology, to understand something about a physics problem. So usually it's the other way around. Usually we use physics to tell us something about a biology problem. We build a better microscope or better simulation and so on. But here we did it the other way around. And I thought that was really quite remarkable. The student who worked on this was doing, as most of my students do, a physics problem and a biology problem simultaneously for her PhD work. And we discovered that they were actually the same problem. All right, well, I'm going to leave you with some references to the work that I talked about, and I'll be happy to take any questions.
Steve?
Thanks, Nigel. So I don't know how literally to take your statement that the critical point of the transition is at zero roughness, because that acts like a magnetic field, and infinite Reynolds number. So does that mean that, if you had a really super smooth wall, that there's not some Reynolds number where it just inevitably becomes turbulent until you get essentially to infinity? Or
so this fixed point is controlling the fully developed turbulence. The roughness going to zero, Reynolds number going to infinity, is controlling the fully developed turbulence, not the critical behavior here. I didn't talk about the effect of roughness on the critical behavior.
I see.
And what this affects is this. Here, these data, this is what I want. So what's happening here is the friction factor becomes independent of the Reynolds number. So what that means is this: as you go to large Reynolds number, what you are doing is you're taking the viscosity goes to zero. So as the viscosity is going to zero, you would think that energy would be conserved, and so there would be no dissipation. But that's not what these data are showing you. These data are showing you that as I take the viscosity going to zero, there is always a non-zero dissipation in the system. And that limit is the first anomaly that was ever found in physics. It's called the dissipative anomaly. It's just like the anomalies that you get in the chiral anomaly or other things that you get. And this is what you're seeing here. And that's the singularity that I'm telling you about. As the roughness goes to zero, you go further and further down this curve here. So we can think of this as a sort of weak anomaly, and this is as a strong anomaly. Those are terms that my collaborator Greg Eyink likes to use.
I see. Thank you.
Does that answer your question?
Yep. Thank you.
Yep.
Maybe this is a follow-up question. You mentioned that the predator-prey dynamics, as naively written down, have an anomaly in them. Could you expand on that a little bit?
Sure. Yeah, let me scoot up to where I talked about that. Down here. Right. Here we go. So yeah, if you take so everything I told you about how predator-prey ecosystem works would tell you the following. If I have an ecosystem, I should write down the Lotka-Volterra equations that describe how the predator and prey interact, and some of you will know those equations, and the standard equations that people who teach differential equation courses use. But then if you look at those equations, you'll see that they don't have cyclical solutions. Their long-time behavior are fixed points rather than limit cycles. Okay, so the problem is this: usually when those equations are presented, you ignore the carrying capacity in the system. So you just say that the system can support an infinite number of predator and prey, and you solve the equations, and those equations turn out to have a conserved quantity. And so you get orbits, but the orbits that you get in predator and prey phase space depend on the initial conditions. They're not limit cycles, they're not long time attractors. So then you say, okay, well, that's fine. Now let's put in the finite carrying capacity. The field can only support, 50 sheep or whatever it is. And then what you find is that the solutions to those equations are fixed points, and that's shown over here. Here you can see what happens when you solve the equations. You just get a fixed points solution here. So these equations are very strange. The periodic behavior in the equations without carrying capacity do have cyclical behavior, but they're not structurally stable. And the minute you put in any amount of carrying capacity, those solutions disappear. So the ecologists said, well, darn, that's terrible. Maybe we need to put in more biological realism. So for example, maybe we should put in the fact that the predators can only eat a certain number of prey, they can't eat an infinite number of them, and so they put in some extra physics that puts in, or extra biology that puts in some extra nonlinearities, and those extra nonlinearities then give you limit cycles. So you're kind of happy, except that you should be very unhappy because you didn't need to resort to this extra biology in order to convince yourself that the behavior should be cyclical. And in fact, if you take the system and just do a Gatsby simulation and just simulate it stochastically, you find that you get perfectly good stochastic simulations, the stochastic oscillations. So what's happening is when you look at those cycles, this is unpublished work that I'm doing with Shilling, but when you look at the differential equations with infinite carrying capacity and then with finite carrying capacity, what you find is that that the behavior has a singularity. There's anomalous dimensions associated with that, and what's happening is that there is a singularity. The limit of carrying capacity going to infinity is a non-analytic limit, and the classical limit of the stochastic theory, where you take the weak noise limit, turns out to have an anomaly, and that gives rise to these stochastic oscillations, which are noise driven. So it's a very subtle subject, and you can see here, what's happening here is that the solutions of the deterministic equations have these ringing oscillations that decay to zero. And what's happening is that the fact that the predator and prey are quantized, they have birth and death processes that occur in integer values. The shot noise from that is what excites these persistent cycles. And so the description of that, it turns out to be the way I'd phrase it is as an anomaly in the stochastic field theory. So we're still in the middle of doing that, but that's the connection. Does that answer your question, Ben?
Yes. Other questions? Well, let's thank Nigel again. That was a fantastic talk.
Thank you.
Yay.